There was many things about, especially focusing on reorgs.
We can't sacrifice decentralization and liveness. These are just number one.
Mainnet is about 40% nodes on the cloud, and you could assume that these 40% nodes are gigabit connected.
I very much recommend Xatu.
But also at the same time, even if you're not running a node or you don't want to run that, just getting vocal on Twitter.
Once we apply some more optimizations, it could help us scale even further.
Ethereum's rollup-centric roadmap depends on layer 2s, and with the Dencon upgrade live, we are seeing the real-world impact of blobs. But with demand, challenges grow as well. How do we scale Ethereum efficiently without sacrificing decentralization and network health? Stay tuned to learn more. Welcome back to PEEPanEIP, where we learn about Ethereum's improvement proposals and latest research shaping Ethereum ecosystem. This is episode 143, brought to you by Ethereum Cat Herders, and I'm your host, Pooja. Today, we are diving into EIP-7691, the blob throughput increase, which aims to provide more scalability for rollup and infrastructure provider by increasing the number of blobs per block on Ethereum. Co-authored by Parithosh Toni Sam, Calder-Mason, Andrew Davis, Ansgar Dietrich in April 2024, EIP-7691 is set to be included in Pectra upgrade. If you are wondering what EIP-7691 is and why it's being considered for Ethereum upgrade, you're in the right place. So joining us today to break it down are the co-authors of the proposal, Parithosh Sam Calder, Toni Introduction. Welcome to PEEPanEIP.
Hey, thank you for having us.
Yeah.
Thank you for joining.
Thanks also from my side.
It's been fun talking to you guys offline and having you here. But before we dive into the proposal, could you briefly talk about yourself and tell us what you are currently working on?
Sure. I can go first. Hey, I'm Parithosh. I work at the Ethereum Foundation Panda Ops team. And most of the stuff we do is testing as well as coordination for forks. So all sorts of things that is required to make sure that the next Ethereum fork happens securely and safely.
I can go next. I'm Sam Calder-Mason. I'm on the same team as Parry, so we work on a lot of the same stuff. Currently, our main focus is obviously Pectra, given it's a few weeks or months away. But specifically, I'm more focused on like the network observability stuff, metrics, alerting, that sort of realm, and starting to now dive a bit more into the analytics world. Over to you, Toni.
Yeah, and my name is Toni. I'm with the Applied Research Group at Ethereum Foundation. Recently have been very involved in research around the blob count increase, but also the gas limit increase. And very recently looking a lot into execution layer research, like delayed execution, block access lists, and that kind of stuff.
Awesome. Thank you so much for sharing about you and your work. Now that we have got introduction covered, without further ado, let's peep in.
Okay, so today we're going to be talking about EIP-7691, the blob throughput increase, as well as all the groundwork that went into making sure that we could realistically scale the blob throughput of Ethereum. So the first question that often comes up is why scale blobs? The Devnet as a fork itself was roughly a year old, so it's not a drastic amount of time, and we're already talking about increasing the blobs. The main reason is that Ethereum has an L2-centric roadmap. So L2s are the predominant users of blobs today, and L2 usage is on an upward trajectory. We have app chains, base themselves are scaling up to 250 megacache. We have Arbitrum, ZK Sync. We have a lot of different L2s who are all independently scaling their own throughput, as well as a lot of applications and other people deploying L2s themselves. So there's been a huge demand of blobs over the years. And when Devnet as a fork happened, it was the first time we were introducing the concept of blobs. So naturally, we were relatively conservative with what values we chose for the blobs themselves. So the L1 needed to figure out scaling these blobs and ideally scaling these blobs reliably over the years. Failure to do so basically limits the L2 ability to grow. Sometimes the L2s do fall back on using call data, but ideally they don't. And ideally there's enough blobs and they're cheap enough that they don't have to think about this or worry about this. And everyone likes the cheap transactions that the roadmap promises. So it is something that Ethereum aims to continue delivering. And there are, of course, a couple of blockers. We can't just suddenly increase the number of blobs by, let's say, a factor of 10, right? So we had to first think through what the problem sets could be. A large one that was brought up on all core devs for a few weeks or months at a time was recovery post non-finality. So Ethereum's always built to be resilient against the worst case scenarios. So what if there's a client bug? What if there's a minority client bug, majority client bug, whatever? We need to be able to recover from this. And we need to be able to offer that home stakers are also able to perform under these scenarios. They should always be able to sync, produce blocks, and on average, we want to maintain that Ethereum has a very low reorg rate, so it's reliable and safe to use. The other topics were how do we collect this data reliably? So of course, we can spin up a bunch of nodes on the data center and then claim that a 10x, 100x is fine, but that's not reliable collection of data in itself. Once we collect the data and find a way to collect the data, we need to also analyze it and try and find the constraints that the chain has. So I think all of these blockers are what we're going to be talking about today across the three of us. So to address the first one, the edge cases of how the chain looks, we had a line of devnets at the end of last year called non-finality devnets. Fun fact, we also just named them NFT devnets in the beginning because we didn't know what we would find and we didn't want people to immediately go digging around. Ethereum itself has a concept of finality, which allows it to be live but not finalizing. This implies that you're able to continue using Ethereum, even though the version of Ethereum you're using has not been checkpointed and never irreversible, right? For example, if there's a bug in a majority client or a client that has a decent stake in the network, and under these conditions, you might even have multiple forks of Ethereum, but the chain keeps running. However, once the bug has been fixed, then all of these clients or forks would need to converge on the same version of Ethereum, and they would need to finalize again. But now imagine a world in which we increase the blobs so much, or the gas, or whatever parameter we're talking about, that the process of downloading and syncing these good blocks might just exceed the rate of production, or even the process of verifying it might exceed the rate of production of these blobs. Now, if that's true, then we can never realistically recover from a non-finality event. So there's no path to safety, so to say. And this is extremely scary. It's an edge case we want to make sure that we never cause. It's an edge case we want to make sure that we're not in right now and potentially will never be in. So in order to test our hypothesis that this is not what Ethereum looks like and increasing the number of blobs won't put Ethereum in this space, we set up a devnet. It was a very large one. So there were close to 600 nodes, if I remember right, roughly 1 million validators. So equal to / representing mainnet Ethereum. We also used the client split offered by clientdiversity.org. And what we did was at every experiment, we would have a healthy network. We then had a few hours or days of non-finality, and then we healed the network again. And once we healed the network, we would analyze how long it took to heal. And just to note, this is in a clean EL state. This basically means that the execution layer block verification and state access, etc., didn't cost a lot of time. And the second one is that while we had like 600 to, my upper limit might even be 1,000 nodes, we're still talking about 10 to a factor of 20 lower than what mainnet actually is. So while this test gives us a lot of confidence, it isn't a complete representation of what mainnet would look like. And in order to collect a wider array of data, we did a bunch of different rate limits. So one thing is we had about 5% gigabit nodes, or these are nodes that you can imagine exist in the cloud, and roughly 95% with 20 MB download and 10 Mbps upload, for example. And then we varied each of these numbers until we figured out kind of what are the limits of what the network should support, or what are the limits of the network that we could support. And just to give you an example, based on some measurements, mainnet is about 40% nodes on the cloud, and you could assume that these 40% nodes are gigabit connected. And the rest are a bit harder to trace down, but it gives us a general idea of what is the source of truth. And yeah, we started off with spinning up and down all of these machines. It's a lot of cores, a lot of RAM that we had to rent for a very short duration. The experiments themselves tend to be expensive. So we tended towards pre-planning a lot of things and as soon as possible, kind of ending the experiment. And I can go a bit into what the outcomes of the experiment were. So one thing that we learned almost straight on was our mental model of what the Ethereum P2P layer looks like needs updating. So the first version of the NFT devnets that we had a very low bandwidth limit applied to it, and it was completely flat. And we saw that even without really stressing it, even without non-finality, the network was fine. But post non-finality, the network actually never recovered. This showed us that flat networks help us design for the worst case scenario. However, it's quite unrealistic. You probably will never achieve an Ethereum that has every single node with under 10 Mbps of uplink and downlink, or even symmetric uplink downlink. That's just not how the network looks. We will, however, always have some percentage of these nodes who are in the cloud, and even home stakers who have more than 10 Mbps, who kind of end up doing the brunt of the work, right? So this mental model of flat Ethereum with very low resources probably is not right. We need to update that model. And that's where some of the analysis that Sam and Toni are doing would also play into. So the second one is, on all the scenarios that we looked at, long-range sync time seemed reasonable. So the node is always able to recover from these edge cases, even when we go to a flat network of like 20 Mbps to 10 Mbps. And bit in the next slide, I would be talking about what the conclusion is, but we're always able to recover from the worst case scenario. And 20 Mbps down versus 10 Mbps up tends to indicate recovery limits. I think once you go below this, you're producing stuff too fast in order to be able to catch up to the chain. However, while doing this, we noticed that even on these gigabit nodes, they weren't actually saturating the gigabit, which means they were pretty much at like the 160 Mbps with roughly 5x headroom available there. And this tends to indicate that there's some sort of peering range request optimization that we are missing and we potentially could look into. And one thing we noticed is that when we had a flat network with 100 Mbps down and 50 up, the bottleneck observed was in fetching from multiple peers. We were sort of saturating the 50 Mbit up, but there was a lot more download available, even though all the nodes were not downloading or uploading at the same time. So there really is a bottleneck in being able to fetch these small chunks from multiple peers. And there's some theories out there as to why this is the case. And we're also actually able to measure a flat network degradation. So 30 Mbps down and 15 up, the network starts to degrade around the edges. So the target vote rate tends to drop just a little bit and so on, and noticeably starts to degrade once you go below 20 Mbps download and 10 up. However, this number also is directly related to how many nodes are in the cloud. So once you have like a 40% of the network having gigabit connection, then suddenly the edge nodes could get away with slightly lesser requirements because someone else is doing the brunt of the work. And here's a brief example of the non-finality recovery scenario, how that looks like at least. So the main reason all the nodes don't start up at the exact same time is it just takes time to run these scripts from one machine, especially over dozens/hundreds of machines. But you can see that the trend is quite up into the right, and eventually almost all the nodes make it back up to head and the network finalizes again. And a couple of basic conclusions that we come up to. Clients are not purely bandwidth limited. This is actually great news for us. This basically means that if we have a decent set of healthy gigabit nodes in the network, once we apply some more optimizations, it could help us scale even further than where we are. Long range syncing itself does not seem to be an issue, even at the higher blob counts. So what we did was we kept pumping the network in with a lot of blobs such that it was closer to 4, 5, and sometimes even 6 blobs per slot. And this is indicative of how it would look post the EIP-7691 change. And it seems like the blob fetching as well as verification was not the bottleneck that we were worried about, thankfully. However, there were a couple of future research streams that did come out of this. So blob censorship via map boost, for example, could lead to different recovery patterns because you could see more blobs that were 0, 6, or at the max or being dropped, as opposed to our test, which was more naive. So they were like most slots had some blobs in them. So the load was more evenly distributed. The optimizations of get blobs was mostly not considered. This is the optimization in which if an EL's mempool already has the blob, you could fetch it directly rather than the CL downloading it again. At the time of doing these tests, not all the CLs had this feature implemented. So this is something that by now almost all CLs do have and also helps a decent chunk with improving our throughput. So we will need to redo a lot of these tests to understand some of that. And more bandwidth constrained nodes might actually be needed in feature devnets. So whenever we're doing testing, we probably will be introducing these bandwidth constraints early on to actually understand how an upgrade affects what we imagine the mental model of Ethereum to be. And while doing these things, we also came to the understanding that formalizing these hardware requirements and network requirements is becoming more and more important. We want to operate Ethereum at closer to what its limit is, and it's harder to know what the limit is if you've never defined what the requirements are to run a node. So Kev has been putting a lot of work and showing up at ACD and making all of these proposals to try and standardize what an Ethereum node can be. And it's being done with a roughly 5-ish year timeline. So the hardware that's being recommended, you can expect to be good for about 5 years, along with recommending network parameters. And both of these things together would help give us a much better idea of A, how the optimizations play out, B, what the network layout and topology could look like, and C, if we were to approach scaling from different perspectives, for example, doing blob parameter only forks, how that would look like. And yeah, so most of the outcomes of the NFT devnets, so good news, there's nothing to worry about. Ethereum will be finalizing even at these higher block throughputs. But the question still remains, what is a safe number to upgrade to? So while the earlier NFT devnets were going on, we had EIP-7742, which was a way for the CL to tell the EL what the blob count should be. And this was not implemented on the NFT devnets. And the reason it wasn't implemented and had been a bunch of months of work put into this is that there was quite a lot of intricate details we were missing, tending to be around gas estimation / validation of sync and stuff like that on the EL. So rather than spending more time trying to fix it, around end of November, we decided to go with a more simple approach, EIP-7840. And the EIP essentially introduces a blob schedule. So the blob schedule would exist on both the CL as well as the EL. So it is redundant data that we were trying to avoid. But for sake of speed and simplicity, it's faster to just specify it in 2 locations. And this also allows us in our testing to more easily play around with blob numbers so that we can actually make sure that the network will be fine and that throughput will be hit.
Right, yeah, thanks, Perry. In this part, I want to quickly highlight some of the empirical research that we did. Of course, not only me, that many other people at the Ethereum Foundation, but also at other organizations did in order to, in the end, steelman the blob count increase for Pectra. So for the following, you might just click a few times. This kind of shows you all the research we did there was many things about especially focusing on reorgs, because what Perry just described was the syncing problems that come with more data. But this empirical research more focused on reorgs, not really every missed slot, but especially focusing on reorgs, which means kind of the proposer tried to put a block out, but in the end, the block was reorged. On this slide, we can see on the top chart the number of reorgs over time. And on the bottom chart, we can see the missed slots over time. And here it's way more important to focus on the top part, because the missed slots are basically those slots where the proposer didn't show up. So a missed slot is defined as a slot where we didn't see a block signed by the rightful proposer. So this might be just either validators, proposers being out of sync in their slot or offline. And the top chart showing the reorgs is more important here, because reorgs are actually based on the number of, so there is definitely some dependence on the number of data and how it relates to reorgs. And with a blob throughput increase, we are of course worried that the number of reorgs might increase. Luckily, what we can see in this chart is that since the Dencun hard fork, the number of reorgs is trending down and is as low as it hasn't been for quite some time. At the beginning, when blobs were rolled out, this looked a little bit different. There were some difficulties to resolve at the beginning, but then as of now, the network looks very, very healthy, and we see only very few reorgs nowadays. We see the same basically on this chart, where we can also see the Dencun hard fork happening, and then especially the number of reorgs for professional entities trended down to very low numbers, while for solo stakers and Rocket Pool, for example, Rocket Pool stakers, it remained the same. And the reason for that is basically because solo stakers and Rocket Pool validators, same as many of the unidentified validators, are the users that are heavily using or heavily relying on local building and are not using MEF Boost. And on the next page, we can see this, we can see on the left-hand side, the MEF Boost builders, and on the right-hand side, the local builders, and then the reorg rates. And we can see that while people might often think that solo stakers are doing worse when it comes to reorgs, it's actually the local builders, right? So local builders in a disadvantage because they don't use MEF Boost, which means they don't have access to this very fast block propagation that the relays take over. So this is very important to not confuse in the context of when we talk about increasing the hardware requirements that come with blob throughput increase, that it's most of the times not really the MEF Boost solo stakers that are struggling, but really those, if solo stakers are struggling, then it's most likely those that are not using MEF Boost. This is very important to mention. And on this chart, we can see the evolution of the reorgs over the number of blobs per block. And as we can see is right when Dencun was shipped, so right at the beginning, we see big bars, and then it kind of calms down. And nowadays we have very few reorgs. So now we are at today's reorg rate. And here we can see Perry already indicate that it's very important to also look at the distribution of blobs over blocks. And here we can see that blobs are very unevenly distributed over blocks. So we either see blocks with 0 blobs or we see blocks with 6 blobs. This was way worse right after the Dencun hard fork, and the situation is definitely improving. But nowadays, so as of today, it's still the case that we see either blocks with 0 blobs or blocks with 6 blobs most often. And then Sam will now focus a little bit on especially on one of his research pieces that gave the EIP the final push, I would say.
Yeah, cool. Yeah, so I've just gone over all the research and the devnets and everything. And we have this EIP that's sort of sitting there temporarily, has a placeholder, target, and max, but we don't know what to set that value to. So actually deciding that parameter, the priorities are pretty simple. So we can't sacrifice decentralization and liveness. These are just number one. But then obviously we just want as much throughput as possible. And if you look at the top secret research on the right, like more blob count, more good. It's pretty simple. But we need to pick something that's, not going to break the network. So when you sort of chart how that looks, you've got decentralization on the left, on the vertical axis, and then max blobs on the horizontal. Green is mainnet today. We want this EIP to be in that gold area. We don't want any home stakers to drop off. So we've got to pick where along that, on that gold line or yellow line, we can set the max blobs to. And obviously, avoiding home staker drop off. That's like a horrific outcome for this EIP if it does happen. So just to recap on the home stakers, they're Ethereum's most valuable asset. Decentralization is the whole point. But unfortunately, they're also the most bandwidth constrained, and especially with upload. And this is really unfortunate considering they have to, when they go to propose a block, they have to publish this block to their peers along with all the blobs. So upload really comes into play here. And potentially the hardest problem is for us, it's just really hard to observe how they're performing. We don't have any metrics or data directly from them. Like historically, we can see the blocks that were created by home stakers, but then we would observe them on data center nodes. And it sort of invalidated the data a little bit. And it was an unknown, and there was no real data for this at all. So we sat down as a team and sort of brainstormed some ideas. Turns out we've already got a data pipeline called Xatu that captures a lot of this timing data. So when a block is seen, when a blob is seen on a node, when an attestation is seen on a node, and it all gets aggregated and then anonymized and then published back to the community. And we rely on it a lot internally, but it doesn't have any home staker data. So we came up with a plan to open it up to the community, and a bunch of people from the community signed up. They submitted the form, and now they run a sidecar next to their beacon node that submits this timing data to us in a privacy preserving way. Quick shout out. We're definitely keen to get more data. If you're interested and this sounds cool to you, follow that QR code or hit one of us up and we'll get you onboarded. So we ran this scheme for about 6 to 8 weeks to get enough data, and it offered a fresh perspective on the problem. So finally, we were able to identify the blocks that were created by home stakers and then actually seen on the other side of the network by these home stakers as well, really closing the loop, which was awesome. And this ETH research post was, it sort of dived into the data, and it comes to this final conclusion at the end of why we picked 6 and 9. And this is sort of, the final conclusion. So there's a lot going on this graph. I'll just dive into it a little bit. So this is block arrivals as seen by home users when the block is created by a home user and it's built locally. So no MEV boost involved. And this is worst case, worst case, worst case, worst case. So no MEV boost, which is what Toni talked about before. So there's no relay on the other side proposing and spreading the block on their end as well, which they usually have high bandwidth and they're well connected. So it really helps the home staker. These are locally built blocks, so there's no help there. Solo stakers or home users, they don't have good upload, they don't have good download. And then also on the other side, seen by these same group of users. So we're really talking worst case. And then finally, we just bolt on the absolute worst case block size in EIP-7691, just to really completely cover all our bases. So then on this chart, the black dots on the left, these are the actual individual arrival times. And we can draw a trend line for P95, which is the red one, across. And this means that 95% of the arrival times exist underneath this line. So 5% is above, and we can sort of consider these outliers, I suppose. But this trend line actually arrives a max of 9, which is pretty good considering this is so many worst case stacked on top of each other, and it still supports a bump, which is great. In reality, mainnet doesn't actually work like this. We don't just have locally built blocks, and we don't have bandwidth starved on both the block proposer and the other side of the network. So to sort of reinforce that this is safe, this chart is a bit more realistic. So this is solo stakers and home users, but they're using MEV relay to publish their block. And it's also only using the average block size of the last 3 months or something. And this one, if we do the exact same thing, it actually arrives at a way further, sort of predicted max of 20. So in reality, like what we can actually support safely is probably between 9 and 20. We just can't know. And we'll probably like have a better idea post Pectra. And as we get more data and as more people start contributing their data. But for now, 9 is like the safest. And yeah, it seems to be the best point on that gold line that we referenced earlier. Yeah, that's all. Thank you very much.
Thank you so much, you all, for explaining this. It was very interesting to learn about these many numbers. Pari, you started with sharing about blockers, devnets, and the name of the devnet, NFT devnet, was pretty interesting. Obviously, I understand this is an update to existing specs, so we were expecting a lot of number to, verify why we are getting this number, where obviously Sam's chart, which was very interesting, played a big role there. You also mentioned about hardware requirement of the EIP, which was good. And the best part of it was, it seems like the spec is more or less there for 5 years, because there was some discussion around, how we are going to put the status. Do we need to keep updating these specs and things like that? Perhaps one day we will have a discussion specific on that proposal. That's pretty interesting proposal. So we'll get there. And Toni, you have shared list of so many researchers. Would love to add some or all of those links to our resources section, so people who are interested into diving a little bit more deeper may be able to get to understand these things. So thank you all for sharing all these details with us. All
You're
right.
welcome.
Yeah, it was fascinating. I mean, when we see all these numbers as a non-developer, I can say it may not make sense to me as much as it will make sense to any developer and people who are curious. Fantastic presentation.
I will say that a lot of the analysis and the approaches taken to the analysis is also kind of the first time we're trying this out. I think Sam was already involved in the initial decision for choosing 3.6, right, with the call data tests. Do you maybe want to just briefly mention how that was and how that was different?
Yeah, so when we did 4844 for the first time, like blobs were a completely new concept. So we had really no basis to go off like we do with this. So a couple people at the Ethereum Foundation, we sort of organized a big blocks test where you could essentially fill blocks with transactions that just blew out the block size a bit. That would simulate essentially as if we added blobs on top for those blocks. And then we could analyze how that performed, what the attestation rates were, if it got reorged, for example. I think there was 2 individual tests for this that were done about 18 months ago. And they gave like a rough idea of something, essentially just like, if we roll out 4844 with 3.6, like, is it going to completely blow up the network? And we saw no, but it was definitely like a very early version of, this analysis and this sort of model that we've come to. It was sort of as good as we were going to get, I think. But yeah, it ended up working.
Thank you for sharing. I think that was my very first question. If I remember the number correctly, it was 3/6, and you already explained. I have a question, if you would want to put up that chart on screen very well. This question is with respect to reorg chart, and I noticed that it was with respect to different entities, and we were trying to see what was the reorg situation with different entities. I understand the explanation given there was because it was locally building and not MEV boost, but I want to understand, does it anyway get affected with the number of participant for that particular entity? I mean, participation, does it? Yes, I'm talking about this chart because I see one of them, which is like kind of almost similar. Okay, this is for solo stakers. Oh, wow, that is good. So I was thinking that this is going all consistent and others have more variation. So we're just trying to understand, does the number of participants affect this chart in any way?
Yes, so it's oftentimes difficult to empirically analyze reorgs just because of the many different impact factors, that play out when it comes to reorgs. For example, staking pools nowadays are playing timing games, so they are risking propagating their block a little late to gain more MEV, which also has a significant impact on the reorg rate. And what this chart kind of shows you is that many professional entities as of Cancun could get their reorg rate down to a certain level. And this is mainly because of math boost, right? This is not really because solo stakers are doing worse or rocket pool validators are doing worse. It's mainly because they are those users that are, more rarely using math boost in the end. It just happens to be the case that solo stakers are also the users that are doing local building most oftentimes.
Do we expect with EPBS and other proposals, IELTS proposals, which are proposed in future, may be able to help streamline it even better?
Yes, exactly. So EPBS can help on that front. Then, of course, inclusion lists, because the argument is oftentimes as soon as we have inclusion lists, we have enough power with the solo stakers to still determine the contents of a block, thus enforce censorship resistance. So there are many things that play into that, but I would say the future for that looks kind of bright with all the proposals that are floating around solving that.
Well, thank you. I think my next question is for Sam. In the presentation, you briefly mentioned about home stakers' concern of bandwidth constraints. I understand sometimes when we are talking about spec changes, it may come up with trade-offs. So what are, if there are any, risk or concerns with increasing blob throughput? And do you think it will affect home staker too much, or like we are having enough mitigation plan in place?
Yeah, cool. I think it's just a reality that if we increase blobs, like we will lose a certain percent of the network. That's just naturally how the network is sort of structured. We think that it's at like an acceptable rate at the moment, and this increase, will not make a material impact to these users. I think also one thing that sort of helps us out here and counteracts that function where increase blobs and we lose participants. Yeah, there's other optimizations that are happening under the hood. So Parry mentioned it, the get blobs optimization, which fetches the blobs from the execution layer mempool, which already has them. It's already spent the bandwidth on fetching those blobs. Things like that and other peer-to-peer optimizations sort of counteract this. So I think for this fork, I'd actually be surprised if there's any, if any, sort of drop off or issues for home stakers. But yeah, it's a very complex system. I'd be way more worried if this was like a 3 or 4 or 5 times throughput increase, but it's not. So yeah, should be all good for the home stakers.
Thank you. I think it is good, as you mentioned in your presentation as well, like Ethereum do not want to compromise on decentralization. We definitely will have some loss, but would not be significantly affecting the network. Very well. My next question is for Parithosh, as he has been involved into all testing, devnets, and all sort of things. So we understand that there had been some network monitoring since TenCon. Maybe with an example, if you can let us know what monitoring tools were used that help us get data to indicate that network can safely scale with the numbers that we are proposing with this proposal.
Well, most of the data collection tends to happen via Xatu. So that's what Sam and Andrew, as well as Matty, who relatively recently joined the team, mainly work on. We do tend to deploy a version of Xatu for most devnets so that we actually get this sort of data and we can analyze it ourselves as well. And Philip from the team has built this tool called Gumi, and Gumi allows us to submit blobs at a finer grain level. So we can tell it that we want to see an average of 7 blobs on the network, even if it's higher than the target. And Gumi will try to make that happen. And then we use Xatu to try and visualize how that impacts the network in itself. So it's kind of 2 or 3 tools in our arsenal that we use to achieve the goal. But the kind of downside of this approach is whenever we're looking at devnets, we tend to only have data center nodes. Like, for example, in the NFT devnets, I need 500, 600, 1,000 machines. I reasonably cannot get that at home. So likely I will be using data center nodes. So one thing we started doing around November is using a few of these Linux tools as well as Ansible to apply like a bandwidth as well as network limitation on these cloud nodes. So we can artificially induce latency, we can artificially induce bandwidth limitations and so on. So that goes a decent bit to help, but that's kind of the crux of the problem. So P2P is hard. I don't think we figured out one simulation strategy that's worked, one Devnet strategy that's worked, or one data collection strategy that's worked. It's likely that it's always going to be like a superset of, hey, we've tried 2 to 3 different things. They all point in this right direction. And that's why we made the choices that we make. I do know that the EF is planning on investing a bunch of resources over the next year to help us demystify the P2P layer a bit more so that we can have a lot more guarantees if that's via simulations, devnets, data collection. We're not sure yet, but there's some plans in place to try and make that better.
That is encouraging. And I understand there are some bounties for some other research work ongoing. Are there any bounties for like tool providers or people who may build up new tools?
Nothing right now, I think. If someone's interested in simulations and interested in P2P simulations specifically, I think we'd be happy to talk. But in general, we're still at the phase where gaining the best of what tools we have right now, and we're yet to figure out what the meaningful next step would be.
I would love to share this piece of information with each Simulate team. Maybe we can get someone who would be interested in P2P simulation and may be able to come forward and help us on that. Talking about Ethereum's broader roadmap as we are looking ahead, how does this proposal fit into Ethereum's long-term scaling roadmap, especially with PeerDAS coming up, the EIP which we are expecting with the following upgrade? And I would also love to understand, should infrastructure providers start preparing for further data availability upgrades?
Yeah, sure. So I would say the blob throughput increase now to 6.9 is only a first step. So it's kind of one step we had to take because we realized that rollups have the demand and we kind of need to provide the supply. And then, of course, the next bigger goal should be PeerDAS, which would then allow us to scale the network much further by finally introducing some availability sampling that would then allow solo stakers to still participate without being worried about those linear scaling increases that come with linear hardware requirement increases. And this is then definitely, I would not say the end goal, but this is the next big milestone that Ethereum definitely has on its mission.
Yeah, and I think beyond that, there's also PeerDAS, at least as it's written today, tends to be reconstruction and sampling on like 1 dimension. And there's also longer term plans of doing like 2 dimensions and so on. So I think there's a research roadmap already for a roughly 100x blob increase over the long term. And I think PeerDAS already delivers a roughly 10x improvement over the current state. There's also a lot of discussions about decoupling forks from blob parameter forks. So that's an interesting approach as well. And the main idea is that the type of research that needs to be done for deciding if a blob increase is safe or not is very different from the type of research, testing, etc., that needs to be done to see if a fork is safe or not. There's a lot more implementation complexity, of course, with a fork than it is with a blob parameter change, especially in the example I showed you with the config. Once you change the config numbers, clients will be able to accept it and increase the blob count. So the long tail of the problem is mostly data collection, analysis, rollout, figuring out scheduling and stuff like that. So it's going to be really interesting to see how that plays out. I don't think we've had one yet, but in general, it does make sense so that we can offer these more conservative upgrades, but we can do them more often rather than doing massive jumps every year or every half a year or so.
So we do see a lot of upcoming changes in future.
Yeah.
Very well. While we are talking about this proposal, I understand adoption of any proposal which is deployed on a network upgrade has a lot of importance. We would love to understand how it has affected different teams. And this proposal is not just affecting Ethereum core developers, but also layer 2 rollup providers and other infrastructure operators. Are there any suggestions or guidelines or maybe any checklist that L2 teams and infrastructure providers should be aware of in order to take advantage of this increased blob throughput?
Yeah, I'm not sure if there are anything to be careful about. I think rollups just get a lot of space for posting their data, even more space than they have today. And apart from that, they will not have to think about moving to posting call data again, because this was oftentimes in the discussion that if we don't scale up the blobs, rollups will be forced to move to call data posting again, or even post on some other data availability chains. And yeah, this is kind of also a guarantee for rollups that Ethereum sticks to the mission of scaling vertically through layer 2s.
I think there's maybe one gotcha that we've tried differently this time around. Typically, we've had the target max is symmetric, or like half. So gas limit is 30, 15's target. We've had 3.6 as the blob, and this is the first time I guess we've had an asymmetric number. So we have 6.9. So the update fraction is going to change. This shouldn't meaningfully play a role to L2s, etc., but maybe they have some custom logic that might need some updating. I'm really not sure, but it is a difference as to how we're doing it now as opposed to traditionally.
Right, yeah. So this means that the base fee can scale faster downwards than it can scale upwards. But for rollups, this shouldn't really, get into their way.
Maybe this is a great opportunity for L2 and other infra provider to maybe participate in the testnet and come up with any requirement if they may have. If it is not being compatible, they can suggest like they are looking for some more guidelines and inputs. So it's another good thing to happen. I wanted to ask this thing, I think I missed it earlier, about decoupling fork that you mentioned. Is that with respect to Ethereum mainnet only, right? We're not talking about layer 2 because we will be going with the blobs here.
Yeah, this is just for Ethereum mainnet. So you can imagine in a world where we had this, we could have done a blob increase 3 months ago, 5 months ago, whatever, based on these reorg rate charts trending downwards. We could have said, okay, hey, a lot of problems we noticed at the launch of Denkun seem to be solved. We have this brand new optimization that seems to help. Why not already ship a blob increase while Electra work continues parallelly?
Awesome, thank you. So we have some upcoming proposals how to do network upgrade in this new model. Looking forward to it.
I think the hardest part will be finding out a naming scheme, because we can do a lot of blob parameter increases really quick and we don't have that many fork names left.
Yeah, I think this time we have to get on numbers. Alphabets are 26 only. Very well. We are coming close to the end of the podcast. Do we have a few more sections to go? I just wanted to understand here, or maybe if you guys want to share some message for the community, for those who want to contribute or get involved beyond developers and researchers, stakers and end users, how they can contribute to the discussion and testing around this proposal.
Yeah, I've got a really easy one, and I'm going to shill the Xatu stuff again. It is actually just the best way for like a tight feedback loop with us and with the researchers and with the community. If you contribute your data and run that sidecar next to your node, it's sort of something that we've never had before, and it will do the work for you. So you just set it up and it will sort of complain on your behalf if things start to go badly on your setup. But also at the same time, even if you're not running a node or you don't want to run that, just getting vocal on Twitter or contributing in the ETH research posts, stuff like that is always a really good way. I know that everyone who writes those posts definitely looks at every comment that comes in. So yeah, I would recommend that. And especially around the fork, being vocal on Twitter, things like that, we definitely pay attention to. So I would recommend that.
Maybe to add to that, so as I'm also a very big Xatu user, I can also very much recommend Xatu. Also for validators to use the data to look up their own performance. Because you can basically check when did my blocks arrive in Australia, when did my blocks arrive in the US, and so on. So there's a tons of data ready to be explored and super interesting for every validator out there.
And I think there's also a recorded DevCon session of you showcasing how to use data sets, right?
Right, yeah.
We are going to add those links here. Please share it with us. And we would love for our followers, listeners, watchers to maybe follow all those links and get more information about that. Very well. With that, we have come to the most interesting section of this podcast. recently started a section called a rapid fire question round, where we try to collect answers from you either in one word or one sentence. We'll try to keep it within 1 minute, but if it is not, that's not a problem. We want you guys to go ahead with honest and interesting answer for community. So if you're ready, maybe we can start with Parithosh. What is the key to successful Ethereum upgrades?
Spending a lot of time actually specifying what the edge cases are and then trying to trigger those edge cases on a lot of devnets. And I think having multiple teams looking at a certain problem or a certain fork really helps with that diversity of thought. I remember this really strongly during the merge. While a lot of the devs working on it were extremely worried, but we took solace in the fact that we weren't the only one looking at this problem. There were a group of 50 to 100 devs at the time looking at this problem. So it gives you some sort of confidence and solace in knowing that you're not the only team looking at this, but instead there's multiple teams, multiple angles, multiple approaches to try and make sure that Ethereum is successful.
That's definitely not one sentence, but what do we expect when we are talking about successful Ethereum upgrades? Very well. The next one here is favorite testing related EIP in Pectra.
Ooh, the blob schedule increase, actually. I like that that would be the favorite one.
Favorite tool for Ethereum testnets?
Right now, Dora.
You have been an author and tester as well. So what is easier, writing an EIP or testing?
I really didn't like writing an EIP. I prefer testing.
Your go-to testing strategy?
I like making a lot of lists. So I tend to have really long lists, really long notes, and go from there.
Biggest challenge in testing EIP or upgrade?
Keeping eye on so many different client combinations.
One overlooked testing tool?
Ooh, I would actually say Xatu. I don't think we call it out enough for testing.
A testing challenge you would turn into a meme?
The client diversity. We have a lot of clients to test now.
Your favorite Ethereum meme so far?
Oh, wait, there's a great one from Sam that's just saying, I am a researcher now.
Testing Ethereum in one word or phrase?
Rewarding.
Well, thank you so much for all these answers. These were all great. Very well. So let's go ahead with Sam. So Sam, your favorite Ethereum execution client?
I run them all, but Nethermine.
One word to describe Ethereum staking?
Enjoyable.
Biggest challenge for node operators?
I would say uptime and maintainability.
Most exciting Ethereum infrastructure or upgrade?
PeerDAS for sure.
One word to describe solo staking?
A little chaotic. Yeah, chaotic.
Most underrated Ethereum tooling project?
The Ketosis Ethereum package. I think it has a lot of rep within the core devs now, but outside of the core devs, it's still sort of finding its feet.
One key improvement needed in validator UX?
I think the consolidation stuff that is coming in Pectra for sure will be a big boon.
Your go-to tool for monitoring Ethereum nodes?
Actually, Xatu as well. I use it personally.
One word to describe MEV's impact?
Also chaotic.
Future of decentralized infra in one word?
Complex.
Well, thank you, Sam. Well done here. I was hoping the answer to the question of staking was it would be challenging, more challenging, because they always keep on fighting, as you said, with the uptime and things like that. But yeah, chaotic is there as well. Okay, that we can move on to Toni. Starting now, most exciting Ethereum upgrade right now?
Right now, so we're talking about Pectra, let's say 7702. So the account abstraction pushes happening there.
Key challenges in scaling Ethereum?
Bandwidth.
One word to describe Ethereum's decentralization?
Let's say magic.
My favorite word was beauty. That's the beauty of Ethereum
Yeah,
world.
that's a good one.
Favorite roll-up solution?
Native rollups. Very pilot recently.
Most underrated Ethereum infrastructure project?
I mean, I cannot mention Xatu again, so let's go for kurtosis.
One word to describe PeerDAS?
Near-time future of scaling.
Biggest barrier to mass adoption of Ethereum?
UX.
Most critical Ethereum research focus?
Scaling.
One word to describe the future of modular blockchain design?
Vertical integration.
What drives you to contribute to Ethereum?
The people, the community, and the core values within the community.
Well done. Very well done, you all. Thank you so much for answering all these questions. I hope our listeners may also find it interesting as well as informative. As we wrap up, this has been an incredibly insightful discussion. Thanks to all co-authors for their work in bringing this proposal closer to mainnet deployment.
Yeah, thank you for having us.
Thank you very much. Yeah.
Yeah, thank you.
For those looking for additional resources on EIP 7691, we will try to add as many as possible links in the description section. You may also find links to follow our guests, so please check out description of your podcast as well as YouTube. A huge thank you to Pari, Sam, and Toni for taking the time to share an overview of this proposal, and to all our call participants for joining us here. I would like to express my gratitude to my colleague at Ethereum Calder, especially Akash and Wailing, for their support in producing and coordinating this series for the community. And of course, thank you to all our listeners. If you enjoyed this episode, don't forget to subscribe and share. And we will be back with another interesting proposal or Ethereum research update for you. Until next time, keep building, keep scaling, and keep perfecting Ethereum. This is Pooja Ranjan signing off.